In this video, we're going to be looking at polar curves. So the idea behind a polar curve is that we are graphing a polar function using r and theta, much the same way that we would graph a curve that was written in rectangular form with x and y. So the strategy that is outlined in your textbook is very similar to a strategy that you would use in the xy plane. You create a table with two columns. The first column, rather than being for x, would be for theta, and the second column, rather than y, is for the radius r. You then create a list of values for theta. You plug those into the function to find the corresponding values of r, and then you have an ordered pair, r theta, which you then plot. So it's a familiar strategy. So let's just take a look at a few examples. So the first one, we have r is equal to r sine of theta. So I created a table of values, and in the left column, I took some arbitrary values of theta. Now, when you're plotting these, selecting the values of theta can be very important. First of all, I like to select angles that I am familiar with the sine and the cosine of. Once again, those would be the quadrantal angles. Those would also be the angles that are multiples of 30, 45, or 60, because we should all know the sines, cosines, and tangents of those angles. So I started off with 0, which is right at the origin, 0, 0. That would be an angle of 0, and that consequently has a radius of 0. When you plug theta, you get radius is 4 times the sine of 0. Well, the sine of 0 is 0 times 4 is 0. Then at pi over 4, which is right here, plugging pi over 4 into sine, the sine of pi over 4 is radical 2 over 2. And 4 times radical 2 over 2 is 2 radical 2. Then up to the positive y-axis, we have the angle pi over 2. And so we know we have r is equal to 4 times the sine of pi over 2. Well, the sine of pi over 2 is 1. 4 times 1 is 4. So we have that point. And then finally, over here, we have the point 3 pi over 4. And so the sine of 3 pi over 4 is also radical 2 over 2, which reduces to 2 radical 2. And then back over to pi. So now notice that when we are at pi, so we're on the negative x-axis, we are back to the starting point, 0, 0. We've created a complete circle. So you could take more points than these, and it might be recommended that you take more points than these, but if you're going to get to something that is going to be so elaborate that you're going to have to use multiple points, we're just going to be graphing these in Desmos. But you could take a point, let's say here at 30 degrees, or pi over 6, at 60 degrees, or pi over 3. And the same thing here, multiples of those angles. We could have taken a lot of different angles, and we would have seen that this does form a nice, smooth circle, right? So in general, when you have r is equal to a sine of theta, that's going to be a circle that is going to be above the x-axis, starting at 0, 0. Where it's going to vary is going to be the radius. So the radius of the circle is going to be half of the value of a, or you could think of the diameter of the circle as going to be a. If it was a negative a sine of theta, then our graph would be below the x-axis. That would be r is equal to negative a sine of theta. And likewise, just while we're on the subject, if we had something in the form of r is equal to a cosine of theta, we're going to find that that's going to be a circle starting at 0, 0, but over here, and then r is equal to negative a cosine of theta. It's going to be over here. So this is one type of rectangular curve that when you look at it, you should be able to tell pretty quickly what it's going to look like without having to actually plot all the points. And that's always a very helpful thing to be able to do. All right, let's take a look at the next curve. And so now what we have is another simple curve. This is theta equals pi over 3. I mean, that doesn't even look like the equation of a curve, but it is. So what we're actually graphing here is we want all of the points that form an angle of pi over 3 to the x-axis. Well, that's going to be a line, because every point on this line is an angle of pi over 3 to the positive x-axis. And so even without graphing or plotting a lot of points, we can tell that that's what we're actually going to end up with. And if we, I'm sorry, I forgot to, we were supposed to convert this into rectangular coordinates back here, but I have that right here. I forgot to mention that. So we know how to convert from polar coordinates to rectangular coordinates. So in this previous problem, when you convert it into rectangular coordinates, you can see very clearly that this is the equation of a circle that has its center at the point 0, 2. Right here, 0, 2 is the center of the circle based on this equation in rectangular form. And that is exactly what we have in this circle. All right, so back to this one. If we convert this into rectangular form, starting with theta equals pi over 3, we take the tangent of both sides. And so what makes me think I should take the tangent? You have to try things, try something. We need to try to get this in terms of some of the trigonometric functions so that we can do a substitution. And so starting with the tangent of theta is equal to tangent of pi over 3. We know that the tangent of pi over 3 is radical 3. And so now I'm doing some substitution. I kind of did this the long way. I could have just substituted directly to this, but I wanted to go through all those steps. Tangent, we know, trig identities, is sine over cosine. And we know from our polar rectangular conversions that sine is y over r, cosine can be written as x over r. And again, that just comes from the fact that y is equal to the sine of theta. And is equal to r sine of theta, and x is equal to r cosine of theta. So just solving those for sine and cosine. So we end up with y over x divided by x, y over r divided by x over r, which simplifies to y over x is equal to radical 3. And writing that in a standard form for rectangular coordinates, we would have y is equal to the square root of 3x, which is a linear equation with a slope of radical 3, which would perfectly represent that line. All right, next up, let's take a look at a different type of equation. Here's another straightforward one. These are the types of problems that you should try to just be able to recognize. When you see r equals 3, from an intuitive point of view, you say, okay, I want the set of all the points, all the x, y coordinates that have a radius of 3 from the center, from the origin. Well, that's going to be a circle. All right, so I can tell that that's just going to be a circle because every point on that line has a radius of 3. All right, so that's what the graph is going to look like, another circle. How can we convert that into rectangular coordinates? So starting with r equals 3, if we square that to get r squared equals 9, we can then substitute in x squared plus y squared for r squared, and voila, that's pretty much all there is to that one. X squared plus y squared equals 9, which we know from previous mathematics classes is the equation of a circle with the origin at 0 and a radius of 3. It's in the form of x squared plus y squared equals r squared. Just like the previous one was up here, it was in that same form. All right, the next one's a little more complicated. This is one that you're not going to be able to really intuitively say, ah, yes, this is exactly what this looks like. You'll notice that with these other problems, I kind of ask myself, what do I think it looks like? And I draw a little sketch first. I drew a little sketch here. I drew a little sketch here. I had to actually plot the points here to get the sketch. Now, for this one, I have no idea what this is going to look like. So we have to figure, how can we convert this into rectangular coordinates? And so a nice little trick is when you have r, square both sides. And the reason we want to square both sides is because that gives us an r squared. And we know that r squared is equal to x squared plus y squared. So that's something that we can work with. Because remember, we want to get these into rectangular coordinates. So that it also introduces an r into both of these, which is a good thing. So we can replace r squared with x squared. And then rearranging this, we have r cosine theta is x. That's the definition of x. And r sine theta is the definition of y. So substituting x and y in, well, we have our rectangular equation. Now we just want to put this in a standard form that we can recognize. And so subtracting the 6x to the other side and adding 8y to the other side over to the left, we end up with this. And so you should be able to tell that this is going to be the equation of a circle. The question is, what is the center of the circle? That's what we need to find. And so we're going to do that by completing the square. So we take the x terms, let me put this in green. We take the x terms, group them together. The y terms are grouped together, and we complete the square on each one of those. So remember, to complete the square, we take the b term, which is the coefficient of x. We divide it by 2 to get 3, and then we square it to get 9. And we add that 9 to the x squared minus 6x. But to balance the equation, we also have to add it over to the right-hand side. We go to the next term, which is 8y. We take half of 8, which is 4, square it, we get 16. We add that to the y squared plus 8y, and then we add the 16 to the other side to balance the equation. Well, this is a perfect trinomial square. It can be factored into x minus 3 times x minus 3 or x minus 3 squared. Y squared plus 8y plus 16 is another perfect trinomial square, which can be factored into y plus 4 quantity squared equals 25. Well, again, that is in the form of a circle, in the form of x minus h squared plus y minus k squared equals r squared, where h and k are the coordinates of the center of the circle, which means the center of the circle is at 3, -4. 3, -4. And it has a radius of the square root of 25, which is 5. All right, so another circle. One more here. We have r squared cosine of 2 theta equals 1. We already have an r squared in it. We could just try substituting x squared plus y squared in there times the cosine of 2 theta. That gets a little clumsy. We still have to figure out what to do with the cosine of 2 theta. So we use a trig identity. I'm going to use this trig identity right here. And so we substitute in cosine squared theta minus sine squared theta, and then distribute the r squared. So we have r squared cosine squared theta minus r squared sine squared theta. That can be rewritten as r cosine quantity squared, r sine quantity squared. And so, of course, r cosine theta is x, r sine theta is y. And so we simply have x squared minus y squared equals 1, which is the equation of a hyperbola. All right. And a hyperbola, which is going to look something like that. It is going to cross the x-axis. It will not touch the y-axis. We don't know all the details of the parabola, but it's going to look something, hyperbola, going to look something like that. All right, there are many more types of polar curves. The textbook talks about polar curves, and for most of these, we're just going to simply use Desmos to take a look at these because some of them get very complicated. What you should do after reading through the textbook is you should be able to look at some types of polar curves and recognize what type of a curve it is. All right.